All right, welcome to Astro 127 Week 10 discussion. Um, so the format of today is going to be a little different. We're going to try out a Khan Academy style video. Um, but let's just jump straight into it with number one, part A. We're going to be exploring the difference between the PP chain and the CNO cycle. So I'll just be trying to also make this a review session by throwing in some random information that isn't necessarily being asked of in the question. But remember that these are both methods of hydrogen into helium fusion that is going on in main sequence stars. PP chain is done in intermediate to low mass stars, so about 1.2 solar masses and below. Those stars are dominated by the PP chain, and then for stars that are about 1.2 solar masses and above, those are the CNO cycle dominated stars, where C and NO stand for carbon, nitrogen, and oxygen, because we are thinking of those elements or a single element that transforms between these three different elements as being a catalyst for this reaction. So we have a really nice cyclical, like hexagonal diagram here on Wikipedia. So I'm envisioning this starting in the top middle of the diagram, where a carbon-12 nucleus encounters a free proton or a hydrogen nucleus. It releases some energy in the form of a gamma particle, or a proton becomes a nitrogen-13 nucleus, actually unstable. So it beta decays, releasing this little white particle. We have a key down here, releases a positron, a neutrino, and then beta decays into a carbon-13 nucleus, and so on and so forth. But the main key things that are going on is that over one clockwise cycle, we get 4 protons that come in, 1, 2, 3, 4, and we get out a helium nucleus. We start and end with carbon-12, so this process can go on over and over again. The same catalyst can catalyze many reactions, so we only need a little bit of CNO in a star for this to occur. And along the way, we emit 2 neutrinos and emit 3 photons, so we're emitting some energy in the process, but we're getting a helium nucleus out of this. What this question is asking for is, why is there a high abundance specifically of this nitrogen-14 nucleus on the bottom middle right here? Well, if we head on over to the link on the worksheet and scroll down quite a bit to table 4 and skip over all the PP chain stuff, we can see that in the right-hand column over here are time scales that tell us how long, on average, it takes for a typical one of these 6 steps. So now we have the CNO cycle written out in steps, how long it takes for each of these steps to proceed on average. Now, we're not going to worry about the details about how these timescales were arrived at, but they depend on things like the cross-section of the particles involved, possibly the beta decay timescale of whatever unstable nucleus, if that nucleus by itself is the beginning of the reaction, relative velocities and things like that, Coulomb repulsion. But we're just going to take these numbers as a given. And basically, we're going to look for the step that has the longest time scale. And kind of surprisingly, these just 6 numbers, they have a very wide spread of over many orders of magnitude, even though they all kind of look similar to one another. But for example, step 5 only takes 82 seconds to occur. So on an astronomical in an astronomical sense, that occurs basically instantly. But step 4, the longest time step, takes 300 million years, for an individual one of these reactions to occur. Billions and billions of reactions are happening in massive stars. So this reaction is still happening a lot, but just for an individual nitrogen-14 to combine with a free proton, for whatever atomic physics reasons involving cross sections and relative velocities, this takes 300 million years on average. So because it takes a long time for step 4 to proceed, we get a lot of leftover buildup of the products of step 3, and that namely is the nitrogen-14 isotope. So it is largely a time scale um, arguments. We're getting a bottleneck at the end of step 3 before we can proceed to step 4. And we would call step 4 the limiting reaction, the limiting step in the CNO cycle. All right, so that's all there is to number 1.